Leo's talk was a great introduction to many of the things I'm going to talk about. And so what I'll try to emphasize is the differences. And so here's the layout of my talk. The first part of it, we'll talk about what motivated us, that meaning Simon Billinger's group and my group, to get involved in this problem of distance geometry. And in doing so, we realized we had to work with a problem that's slightly different than the one Leo emphasized, and that is a problem where we do not know the underlying graph. And we called that problem the unassigned distance geometry problem. And it's been around in the literature a little bit, and so I'll point to where it has occurred in the past. In attempting to solve the problem, we looked at the experimental data from the experiments that Simon Billinger was doing at Brookhaven, their scattering experiments. And so I'll show you how we extract distances from those scattering experiments. And what we get from the experiments is just a list of distances. That's it. And from those list of distances, we want to figure out where the atoms are. And it turns out that this is very relevant to the problems that are done in Simon Billinger's group, but also in a variety of other problems. But I'll emphasize the application to atomic structure of nanoparticles today. We developed an algorithm back in 2006 called the Liga algorithm, which is a stochastic buildup heuristic that does deal with the errors in the experimental system. So there are errors in the number of distances, there's errors in the locations, there's missing distances, and still this procedure was able to solve the problem. What we soon realized, however, was that the example problem we used, which was a fullerene, carbon-60 particles, is quite special. And it's special because the number of unique distances in a buckyball is only 21. When really the total number of pair distances, the complete graph on 60 atoms, is 1,770. So what we have is a distance list which is very highly degenerate. And it turned out the Liga algorithm works well for that case. It does not work well for random point sets where all of the distances are mostly, with high probability, distinct. And so the second generation algorithm, Tribond, is an attempt to handle problems where there's a very large number of distinct distances. In both the experiments in Liga and in Tribond, we're focusing on globally rigid buildup. And that's the case that Leo mentioned. But the difference is that we're working always with these unassigned problems. So we have the advantage that we know that for the assigned case, the buildup is possible in polynomial time. And what we showed is if it's a deterministic buildup for the unassigned distance geometry problem, where we maintain global rigidity at every step, then the algorithm is also polynomial, provided the distance list is precise. And then what we wanted to do with Tribond is extend it to higher dimensions and to problems with uncertainties. We've made some progress in that direction in collaboration with Leo and the Brazilian collaborators that we've developed over the last few years. And in particular, Luis Leduino Salas Neto has come up with some nice ideas about how to transform the build-up process we developed in Tribond using continuous optimization methods. So I'm going to go through each of these, starting with our motivation. Before I get there, I'd like to thank the organizers, of course, and also my collaborators that started this problem, Simon Billinger and his group, and then more recently the collaborators in Brazil and Europe who are taking us in new directions with continuous optimization, which looks to me pretty promising. So our motivation, as I've mentioned, is finding atomic structure of non-crystalline systems, isolated proteins, nanoparticles, etc. The proteins for us at the moment are challenging in the sense that the uncertainty in the distance lists in proteins, the NMR distances, tend to be quite large, whereas in nanoparticles, they're not so large. And we're getting close to being able to treat those cases with uncertainties. It's always important to keep track of what's going on with the competition. And we know for crystals, you can do inverse Fourier transform and you can reconstruct crystal structure. More recently, cryo-EM is doing very well and improving rapidly. So that's a competitor for some of the single particle nanostructure problems that we're looking at. However, there are many other situations where we're interested, for example, in the local structure within a crystal. And the local structure may be irregular, and we would like to know the local environment that can control many processes such as catalysis. And in those situations, there's a lot of guess and check methods that are used, including Monte Carlo. Reverse Monte Carlo is, for example, a common one. And quite a few of them are under constrained, and so we can't really be confident in the structures they predict. So the question in general that we have is, given a set of scattering data, can we find initial structures from the data alone such that we can find more realistic global minima without going to making some initial guess? That was the original motivation that Professor Bellinge came to me with. And when we first looked at the buckyball problem, this is what he had. So A here is the experimental data. So this is called a powder diffraction pattern, where you can take a polycrystal of a material which is spherically symmetric. And so the only thing that matters is the transfer of momentum, that's labeled as Q in this graph. And so the challenge is, okay, given this scattering information, and this is kinematical scattering, which means a wave comes in and it reflects off individual atoms. And so the interference pattern that we see on a screen tells us about the distances between the atoms, which act as sources for the reflected light. And so these bumps tell us positive interference, and then the dips tell us negative interference. So this is somehow a fingerprint that has embedded in it the paired distances within the sample from which the scattering has occurred. If we do a Fourier transform, or the appropriate Fourier transform of that information, we get B. And this is called the pair distribution function. It is a list of interatomic distances that have been extracted by doing an inverse transform of the scattering data. And so you can see there's a bunch of peaks here. Those peaks indicate pair distances. So if we take that chunk there, and I should add, this is a special buckyball sample where the buckyballs are in an FCC crystal, but they're rotating. So all of the nearest neighbor interactions or distances are washed out. And so beyond a certain distance, which is the size of an individual buckyball, all of these peaks, which indicate paired distances, are washed out because the interparticle pair distances are averaged out due to the rotation of the buckyballs with respect to each other. So this is a nice trick that gives us a fingerprint of just an individual nanoparticle. Once we have that fingerprint, we can go to work and pull out all the distances that we can. And this leads to the graph, which is in D. And that's all of the data. So when I first saw this way back in 2004-05, my first reaction was, I'm going to prove that is not enough. It just looks like there's not enough data there to reproduce something which has 60 atoms, and 60 atoms have 3 degrees of freedom each. That's 180 degrees of freedom. We only have 18 distances. It looks like it's highly under constrained. And so I was wrong about that. And as time went on, we figured out how we could reconstruct from just using this information. And so the result of our algorithm at intermediate stages is shown in the figures at the bottom right. And this is from just this data. There's no other information input here. And even the number of atoms is allowed to be flexible. And what we do is watch the error in the reconstruction, and the lowest error is the final structure at the top right of that figure. So that was very encouraging. So we went back to, in fact, earlier than that, we went back to the ideal problem. And this is a snapshot of the distance list for an ideal buckyball, C60. And what you can see is that in the true buckyball, there are 21 unique distances, and they have high multiplicity. So the nearest neighbor distance, which is, nearest neighbor between any two atoms, has degeneracy 90. And then there are other distances, say the second neighbor distance, this one here, has, or third neighbor, I should say. The third neighbor distance, this one here, has higher degeneracy, which is 120. So there's a lot of information in these multiplicities. Despite the fact there are only 21 unique distances here, there is enough information to reconstruct the Fullery. And in fact, the Liga algorithm works better when there's a high degeneracy of distances, and I'll try to explain why in a minute. At the same time, we started to apply the method to things like drug molecules, because part of our interest was to look at drug binding and to see if we could reconstruct local distances in a molecule attached to a protein. But it turned out when we tried to do that, Liga failed. It really was unable to treat cases where there were a large number of unique distances. An extreme case of that is shown in the bottom figure, which is a case of a random point set in 2 dimensions, where if you have 10 atoms, you have 45 different distances. And so you get this plot on the bottom, which is now the distance list, where every distance is unique. And so we wanted to understand how we could develop methods that could treat cases with a very large number of unique distances. I'm going to go through how we develop those algorithms in just a minute. But before I do that, I want to define more formally the assigned and unassigned distance geometry problems as we think about them. So the unassigned distance geometry problem, we're just given a set of interpoint distances, and we would like to look for an embedding in a dimension or a realization in a dimension k. And a simple case is shown in the figure where we have a square, and we're taking all of the distances between the 4 points in the square. And on the right, we have the list of distances. There are 4 distances of size 1, and there are 2 distances of size √2. So this is a case of a degenerate distance list. And if we are just given the 4 distances of length 1 and the 2 distances of length √2, can we reconstruct that square? The assigned distance geometry problem, we have the matrix, which tells us the pair of vertices between which each distance lies. And so, depending on how I label these vertices, but this is the distance matrix, and it corresponds, if I can take this information, I can reconstruct the distance, the structure. So in terms of formal definitions, here is the mathematical definition of the assigned distance geometry problem first, and then the unassigned distance geometry problem second. And the key new part of the unassigned problem is I need a mapping between every distance and the vertices in the graph. So I've got to find the 2 vertices at the end of each distance. And so that mapping is embedded in this function g. And so to define the edge weights in my graph, I have to take an inverse of that function, and that gives me the weight on each edge. So in addition to this part of it, which is the assigned distance geometry part, I've got to do an analysis that gives me this, which is the graph. So another branch of the literature on this problem starts with Lemke, Scienna, and Smith. There's a 1990 abstract and a 1983 review. They talk about finding structures from interpoint distances, and in one dimension, they called them the Turnpike and Beltway problems. And there is a literature doing higher dimension versions using either distances or vectors. There's also a vector generalization of what we've called the unassigned distance geometry problem, and I'll get to that later in my talk if I get there. So let's talk about the Liga algorithm and how that works. So it's a stochastic build-up algorithm, and that's how we treated all the errors in the problem. So it starts with an empty box. We gradually build up and repair partial clusters. That means clusters that are smaller than the full size 60. We use the distance list to choose atoms to add. And it's a lot like k-lateration, but we didn't call it that in the, back when we were doing this. And we try to find the best triangle or tetrahedron to add at each step in the process, which again is similar to the K-lateration. However, one difference is that we don't just keep one cluster at each size. Instead, we have a tournament system where we have clusters of 10, usually we have 10 of each cluster size, all the way from 4 or 5 atoms in a small cluster up to the full size of 60. Then we have promotion and relegation methods where we look at the cost of each atom in a cluster. And the cost is measured as the sum of the deviations of the distances in our cluster from that of the distance list. So we build up these clusters. We also do a local relaxation regularly during the process. So there's a whole bunch of fine tuning that goes on. It's not done for each system, but it's done for C60, and then we will take the data and then just run it. It's not fine tuning during the algorithm. So this promotion and relegation is really important. The way it works is we take one atom off a cluster, say a cluster of size 10, and the worst performing cluster is the one that has the highest error in comparison to the distance list. And then we'll take out the worst performing atom as measured by the deviations from the distance list of the edges which are entering that atom. And we take out that atom, we relax it, and then take it down to the lower league in the tournament. And then if we have a high performing cluster, we add an atom, and we do K-lateration. And performance is measured through deviations of distances from the reference distance list. So pictorially, this is what it looks like. We start building up. If we have an error like this might be in one of the level of the tournament. The ones that are in turquoise are badly performing atoms, and so we take one of those out and relegate that to a lower league level. And in fact, this one went down 2 because both of those were bad. And so we ended up with this, and then we added another atom, and it turned out to be good. So this promotion and relegation process goes on for a lot of time. And one of the things we observed in this algorithm, that it sat around forever trying to build up the small clusters. And then once it had a good small cluster, it really ran very fast to find the final fullerene, even with these errors in the distance list. So here's pictorially the way the algorithm works. And I think I've said pretty much all of that. One thing that we noticed early on is that because of the fact we have this structure, that the fullerene is not a generic structure. It's got a lot of symmetry. It's got a lot of degeneracy. And we have to worry about uniqueness of shape reconstruction. And an example of 3 different structures that can be generated from the distances associated with the hexagon are shown here. What we found, however, is that once you get beyond 7 or 8 atoms, it's very unusual to get these kind of degeneracies. We have so many more edges than we have degrees of freedom in the system. Once we get to complete graphs of big enough size, we feel that the chances of these degeneracies are relatively low. But you have to have many more edges than you have degrees of freedom to be confident. So again, here's the way the solution came out using that algorithm. And as I said before, a key limitation of Liga is the random selection of edges to try, which works okay with C60, which has only 21 different edge lengths, but it becomes very slow as the number of different edge lengths increases. So we tried to develop a method that was more deterministic so that we could build up in a systematic manner. And that was the motivation between Tribond. And it's based on lots of prior work. And 2 of the ones that we really found useful were the original paper by Bruce Hendrickson. And he thought about how to use maximally rigid subgraphs first in build-up. There's also the paper by Dong and Wu that was referenced earlier by Leo, which talks about K-lateration, and we wanted to work with that as well. We also motivated by the work that Khalili Labor and Leo and many of the people in the room here have been working on discretizable molecular distance geometry problems. And in our thinking, we think of K-lateration as globally rigid buildup, and the ones which are discretizable as locally rigid. Locally rigid structures, sometimes called something else, but they're not globally rigid, and they have a certain combinatorial degeneracy. So we're focusing on globally rigid buildup because we think that within the PDF community, it is possible to get enough edges so that we can do the globally rigid approach, and that's more efficient, especially as we have the unassigned case to deal with. So here's how the algorithm works, and really this is following pretty much the same story that Leo told in the early part of his talk. But one difference is we're starting just with a distance list. We don't have anything to build from. So I mentioned already that in the Liga algorithm, we found that the early stages of the algorithm were horrendously slow. And that's because you can't be confident in a structure until you have a certain size of structure where you have a redundant bond. And so a core we define as the first clique in dimension K that has a redundant bond. And the size of that core is K plus 2. So when we're doing precise distances, we would start with a core of this size. Once we start moving to distances with errors or intervals, we have to have bigger cores in order to have enough confidence in our structure and enough constraints on the next atom we add to feel confident that we're building up something that is topologically correct. So we have cores, so we're going to do a search, a combinatorial search, just on the distance list to see if we can find a core that is compatible. And as part of that, we have to worry about whether we're generating structures that do not occur in the final carbon 60, for example, or whatever structure we're trying to reconstruct. And so we define something called a generic distance list. And a generic distance list, and the easiest way to state it, is that if you find a clique of size greater than K plus 1, compatible meaning that there are no conflicts, meaning that all the distance fit exactly, even when there are redundant bonds in the clique. If that occurs, then there will be then that clique must occur in the correct structure. If the distance list is generic, that every clique we can construct without error must occur in the final structure. There is the possibility, and we can construct very easily cases that violate that. And we don't have a theorem yet to say how hard it is to have generic distance lists. However, what we do know is that almost always from random point sets, we are able to construct, and we almost never find cases where we generate a K-lateration, which is not part of the final structure. So our practical evidence is there, but it would be very nice to get a theorem related to that. Having said that, once we have that hypothesis, then we make the statement that the unassigned distance geometry elementary build-up process, the algorithm, leads to a unique reconstruction if the K plus 1 sites in the existing structure do not lie in a Euclidean subspace of dimension K less than K. So in 2 dimensions, it means they can't lie on a line, and in 3 dimensions, they cannot lie on a plane. And the distance list is complete, generic, and precise. Then we are able to build up the structure exactly. So it's easy to show just from the combinatorics, and this is a very loose upper bound, but it's easy to, just from the number of edges in a given distance list, given a size n, complete distance list, that this build-up process for unassigned distance geometry is polynomial. And so that's reassuring. We know that globally rigid build-up is polynomial for the assigned case. It's also polynomial for the precise unassigned case. What about in practice? So this graph I really like because it shows just how important the early stages of buildup are. So it separates out the core finding part, which are the pluses. They're kind of embedded in these circles. Sorry about that. But this is the core buildup part. And this is the part which is the k-lateration. And you can see that the core buildup for this two-dimensional case of random point set is about an order of magnitude more time-consuming than the entire k-lateration buildup. And this is up to 512 sites. So it took more time to put together, and in the plane, the 4-atom clique is the core. And so finding that a correct 4-atom core took an order of magnitude more time than the k-lateration starting from that core and going all the way to the full reconstruction, which in this case was 512 sites. So that made us realize that we can advise experimentalists about, if you want to help us reconstruct, or if you want to try to reconstruct the structures in your system, you could imagine putting in clusters of atoms, say a rigid particle of some kind embedded in your system that you know exactly the distances of. You can use that as a reference, a core from which to build. And this hasn't been implemented yet, but I think it's promising. The other thing to think about when looking at this is that the timescale here for this reconstruction is just over n cubed. That's not great, but it's a lot better than an exponential, and a lot better than the upper bounds that we have. So we've run this for fairly big systems, up to 1,000 atoms, which took about a day. And so the limiting problem here is now trying to figure out how to put in errors. In 3 dimensions, it's a lot slower. So we were only able to get up, or we only went up to about 100 atoms using tri-bond as is. We also generalized it to try to do cases with imprecision. And so this is the 8-digit precision, 7-digit precision, 6-digit. So here, even here, we have an error which is only 0.01%. Nevertheless, we were not able to do reconstruction without starting with significant core sizes. So to get reconstruction here, we had to start with a core size of 9. And that makes things very difficult. It says that this process is not promising, and it is kind of answering Henry's question to Leo. This build-up procedure looks like it's not able to handle this very well. So we stopped there a few years ago, and in the meantime, have been talking with our friends down in Brazil, and they, in fact, it was Louise who suggested converting this to a global optimization problem. In fact, our goal was to try to use global optimization for the whole system, and Louise tried that, and it didn't really work. So instead, what he did was reformulate it as globally rigid buildup using a continuous optimization solver at each k-lateration step, and also for the first step, the step of forming a core. So how did he do that? Well, the first trick was, here is our cost function. We're looking at the deviation between the pair distance and the reference distance in the distance list. And there's this new binary variable, aijk, which does the assignment of a distance to a vertex pair. And so we want to minimize this function over the variables aijk and the variables xi, xj. That looks horrible because we've introduced this massive number of binary variables. And there's other constraints here that are required to make sure that the solution to this optimization problem reproduces the target that we want. So this is the way in which the assignment is done, by using these variables and optimizing the whole function. So the next step is to say, okay, let's convert this to a continuous optimization problem. So this is the Simp method, which I actually am not familiar with, but I'm told it's an important problem. The key thing is that there is now a constraint on the binary variables, which is relaxed to an interval, on the interval 0, 1. And so it was proven by Khalili and Leo that this optimization problem gives the same answer as our original problem. So we have this formulation, which is a continuous formulation of the globally rigid buildup, but it is not yet in a form which can be used for globally rigid buildup. This is just the whole problem. And so Louise tried to solve the whole problem using this, and frankly, it was only able to get up to 9 or 10 atoms. So what we're calling now is tribond C, where this exact buildup that we were doing using k-lateration, we're basically using k-lateration again, but we're solving the combinatorial problem using this Simp formulation. And so it's the same thing, but now these sums are up to 5 atoms. And so this calculation here is the calculation where the core is found. It's going up to 5 atoms in 3 dimensions. And in 3 dimensions, the first clique, which has a redundant bond, has 5 atoms. So there's an optimization process here where we find the best core, optimized core. And then after that core has been found, there's a solution which does k-lateration using this Simp method. So in my way of thinking, and this is just my way of thinking, why would we ever expect this to do better than doing a direct combinatorial search? And that's fairly familiar when you have a combinatorial problem and you can expand the domain. Interior point methods, for example, where you can say, okay, I'm now relaxing the combinatorial constraints, and in doing so, I've made the cost surface more amenable to movement across it. That's at least how I understand it, and Leo may have some input about that too. So what are the computational results? So it's a model protein problem that, again, Leo spoke about a little bit. It has a complete set of distances for the configuration. And then the system was solved using ample within Barron. And model 3 is this globally rigid buildup using Simp. And what you can see here is that it's able to go up to 400 atoms. And this is in minutes. So you can see, it took 10 hours, but 400 atoms in 3 dimensions for this problem is pretty encouraging, and this was on a laptop. So this has the potential to be very efficient for large 3-dimensional, globally rigid build-up kind of problems. So I'm encouraged by that. We haven't yet run it on the data from the buckyball, but that will be something we want to try next. And to do that, we need to have something to do with errors. And so Louise recently has been able to extend the method, having an interval of noise, which has a 1% deviation either side. And here's what he did. He used ample with a solver, Dell notebook. And what you can see from this is that even with this, what might be considered rather small noise, 1%, the computational time taken is increased quite dramatically. Despite that fact, he was able to get to 40 atoms in a not unreasonable amount of time. And I think this is very promising, as there's a lot of things we can think about doing to improve the speed of this algorithm and the number of atoms to which it can go. I also want to add that the errors typical of PDF distances are of the order of 1%. So this is already in the range that's interesting for the problem we started out being interested in. So I think this is a good basis for future work. So what I want to do now is talk a little bit about vector problems. Vector problems are cases where instead of being given the interatomic distances, we are given the vectors. So we can have assigned and unassigned versions of these, and these have been looked at a bit in the literature that follows on from the original work of Lemke, Skinner, and Smith. I'll just talk about globally rigid buildup with vectors. And the overarching message is it's easier than the distance case. We have more information. And in fact, we can transform it to the distance case. So in the case of scalars, which is the distance geometry case, we have the discretizable scalar case where you have, say, this triangle which sits there, and it can be flipped over. So in 2 dimensions, to spatial embedding dimension 2, this system, without any extra edges in here, is locally rigid because I cannot deform this node, but it's not globally rigid because I can move to this other geometry, which satisfies all the constraints, and it is also locally rigid, but it's not globally rigid. And so we're always talking about globally rigid buildup, but it's good to understand what the discretizable case is because it's one step before global rigidity. In the vector case, we are given a vector, which is in a direction, but we don't know where it's located. So here's a vector, and I could have the vector pointing that direction or this direction. And so I can define a discretizable vector case in that way. So from the point of view of PDF methods, there's a push now to try to get the vector PDF, meaning that instead of just getting distances out of the data, we will get some piece of the vector information. And once we have that, we can start thinking about how to apply these methods to build up with vectors. And it's relatively straightforward to say, okay, we have angle constraints in vector problems. So let's say I have this angle. I can think of that as an implied edge. With that implied edge, I can talk about the vector problems having more constraints and follow through on that and do some analysis of what the efficiency of these algorithms will be if we extend them to that case. So the vector geometry case has a similar statement about the possibility of globally rigid buildup, and it has stronger bounds on the speed of the algorithm for the unassigned case. So we call this tri-vec. Unassigned tri-vec is the tribond version using vectors for the unassigned case, and this is the tribond version for vectors for the assigned case. And the bounds here are stronger than those for the distance geometry case. So I'm starting to wind up here. So Leo, I'm happy to say that you took time and it didn't cause me any problems. So unassigned interpoint data are essential to many problems, and there's a long list here. Even in the NMR case, the assignment experiments are kind of difficult and time consuming. If we can figure out how to do the experiments so that we get more precise experiments that are not assigned, then we can use these kind of globally rigid build-up processes. Our first target, though, is pair distribution function data. And we're just about at the point now where we can develop an algorithm that can be used for that purpose. For precise, generic, complete distance list, globally rigid build-up works for both the assigned and unassigned cases, and we have a good algorithm for that. We have the stochastic build-up, the Liga algorithm, that works for experimental data from, say, C60. There's an opportunity here to combine the two. We can probably do a lot better than the early stages of Liga, which just randomly selects edges. So a way forward is to try to use the ideas that have come out of what Louise has developed, these continuous globally rigid build-up ideas, to try to get the core, and maybe something larger than a core for intervals, to use as the starting point for Liga type approaches that build up with tournaments and backtracking. We can also do globally rigid vector buildup, which is actually easier than the distance case or the scalar case. And so that's a direction that we can look at too. The discretizable case is really important. There's a lot of motions that occur in biology that are similar to this discretizable motion that's been studied there. And so I think that's a different direction. The flexibility of those molecules is really important for life. So I think that the discretizable case has a lot of applications that do not apply to the globally rigid case. For example, when you put a drug into a flexible region of a protein. So there are a lot of open questions I would love to answer theoretically. And we know, as I said, that globally rigid buildup is in P. So what about the generalization to distance lists that are not complete? So I think it's true, and everybody would probably see quickly that if you have distance lists that have sufficient edges that we can go through this process of k-lateration, we will end up with a final structure. But what is the speed of that? And how does it scale with a number of atoms? And then we have to worry about, as in the fullerene case or C60 case, we have to worry about distance lists that are not fully generic. And it's turned out that in all of our calculations, both in the random point sets and in molecules and in C60, the lack of generic properties seems to be fairly infrequent. And I think it's because we are looking at distance lists which are complete most of the time or with very large number of edges. So there's an interesting question here around when does this non-generic property start to be important for the problem? We can make the buildup globally rigid, but if there is some non-generic property, then that may lead to some atoms that are placed in the wrong locations, and then we have to backtrack. And the Liga kind of thinking will help with that. So I think we have ways forward which will mitigate these, but it'll be good to understand what the interplay is between the number of edges and the deviation from fully generic. Probably the most important and interesting thing happening right now is this continuous formulation of tri-bond. And I see that as a first step. I'm sure that there'll be other ways to do this continuous formulation that are better, and that we can maybe do a better job of putting uncertainties in, be they intervals or Gaussian errors. And so that's got a lot of promise. There's a general question that I ask myself a lot, and that is, we know that these globally rigid buildup processes are in P. Okay, so now we start adding intervals. Does it immediately go to a hard computational problem, or is there an interval size at which that occurs, or is the interval size at which it occurs dependent on the size of the structure? I would think maybe it's the latter, but it may also depend on the number of edges we have beyond the number that is required for globally rigid buildup. And then finally, which I don't want to say anything on a less than optimistic note, but we know that the best methods for finding atomic structure at the moment are global methods, and they are using crystals and using inverse Fourier transforms, and then the nice algorithms that are out there for cryo-EM and lensless imaging, which takes scattering data, say from LCLS, and produces a scattering pattern which is inverted using direct methods. And those three methods all have nice properties, provable properties. Is there a way that we can combine that knowledge with what we're doing in distance geometry to build systems that have both the advantages of both? So these are all things that are on my mind, and if you have any thoughts, it'd be great to hear them. Thanks for your patience and for listening.
Thank you very much, Phil. Are there any questions from the audience?
Yes, I have a question. Phil, is there any gauge or is there any knowledge about the difference between having all of the distances equal and all of the distances different? Meaning, is there any complexity result, even if in P? I mean, what changes from one to the other in terms of best case or worst case complexity? I know you've worked in percolation, for example, that identified a phase transition in certain phenomena. Could there be a phase transition in going from all distances being equal to all distances being different?
Yeah, that's an excellent question, Leo. And as I said, at first I saw all these distances that looked the same, and it seems to me that they weren't really different constraints, but they are. It turns out there's enough constraints there to solve the problem. And we don't have a good theoretical understanding of that. And there are no results that I know of that talk about the complexity of degenerate distance lists compared to those where all the distances are unique. We only have the heuristic information. And so that's an area that I think is very interesting, and it's related to the hexagon case, where you can see different variants. So you could imagine if you're doing k-lateration and you run across something like that, it might screw up the buildup for a case that has special symmetries. And so we have no information about that. I think it's geometry dependent. That's the problem. And so it'll be different for a cubic lattice than a FCC lattice than some other structure with symmetry like a fullerene. So I think it'll be a case by case, and hard. I don't think anybody's even attempted to do that.
Right. Thank you.
Phil, in the past you worked on the Lennard-Jones clusters, right?
Yeah.
And this is one of these cases, right? It's very symmetric.
Yes, some of them are very symmetric. Yeah, and LIGO worked pretty well with those. We haven't tried a tri-bond on those, but we have tried a lot of drug molecules with tri-bond. And it works fine. It occasionally we have to say, hey, that didn't work, we backtrack. But in most cases, 3 or 4 attempts at most, and we end up with the right structure. So I think it's pretty robust empirically, but the theoretical underpinning is lacking.
Okay, I see. Other questions from the audience? We have 5 minutes.
Yeah, I have a question. That model that you put up, oh, by the way you spelled my name reminds me of something. No, it's no problem. It just reminds me that my first job, I had a different name on my office door, a different name on my mailbox, and a different name on my house door. And the people who put the names there all spelled them wrong. So they were all wrong. Nobody spells my name. Oh, okay. Actually, you had the way my brother spells our name. A different bureaucrat spelled our name and when we entered Canada. So everybody in my family had a different spelling.
Yeah, I go through that too. My name is Duxbury, and you can imagine the misspellings of ducks and berry.
So I was wondering about that quadratic model that you had, the t minus the summation of the sum of squares as an objective function.
Yeah.
Yes. So just one minor question and then another. Instead of equal to t, why not less or equal to t? I would think that less or equal to t would be in the constraint underneath the objective.
Yeah.
Less or equal to t, more.
Good question. Leo, do you have any understanding of whether less than or equal to t would give the exact same solution?
I think it would. I don't know. I mean, we reasoned about this formulation a long time, and then I finally convinced myself that it was correct. I don't remember whether the equal was. I mean, just by my memory, it would make sense that you could relax it to less than or equal to. But I don't want to risk it. Let's keep it equal.
Yeah.
I can see why.
And the other question is, of course, this is because of the objective, you're subtracting a convex function. So, and you're minimizing. So this is a hard problem. So there's, I guess, two questions. One is, are you solving it with a relaxation? Are you solving it as a global problem? Or are you solving it maybe as a, this famous difference of two convex functions approach? I guess there's three questions there.
Yeah, that's a good question. I don't know the methodologies in Barron. This is outside my, I'd love to know. So ample, I'm not sure how ample works. I assumed it was a global optimizer. I believe it's a global optimizer, but I don't know how it works.
Ample is a modeling language, and if we're I don't remember, but if we're calling Barron, I don't know. I think I noticed K-nitro. So if it's K-nitro that is being called, this is a local NLP solver, but it's a very good one. And I wouldn't be surprised if it had some heuristics for sort of trying to get over hills or something like this. So
I think K-nitro is just, like you said, a local.
Yes.
It would just give you stationary.
My impression
it
is
wouldn't do anything about global.
Yeah, we're probably solving this locally, but in the math heuristic, this works because at each step is not a huge formulation, and so it kind of works.
Okay.
We tried to solve it locally, as far as I remember, globally, sorry, and this is what took such a long time for just 5 atoms or less.
Right. So I would. Of course, I'm always being antagonistic, so please don't take this seriously, but just because of conversation. But I would think that if you're solving it, because you have a concave objective essentially, because you have linear minus convex. So that means that every stationary point is a critical point, which means K-nitro will just stop at the first stationary point.
No, I think this is where you're wrong. I think you're reasoning about the theory of local NLP solvers and not the practice. So in practice, many of these solvers have been worked upon so that they can do a little better. They have reformulations that change the KKT points, for example. They stretch, they add slack variables. They will do many different things, and I'm not such an expert on every one of the local NLP solvers that I use, but I do know that they do not necessarily some of them they do find quite good optima. Okay, take as a counter debate point, take a spatial branch amount solver, okay, like Barron. Okay, so in general, and this is a big if, okay, but in general, what happens is that you will find the global optimum early on or reasonably early on in the search, and then you will spend ages and ages and maybe the age of the universe trying to prove it optimal, okay? So this is what happens in general for human problems, not even average problems or random problems, okay? But if this is the case, because since the point is that it is the local subsolver that finds global optima in a global solver such as Barron, okay? So that means that these local subsolvers are finding global optima without knowing that they're global, but that means that they don't necessarily stop at every KKT point, okay? So my impression is that the vanilla implementation of any solver as described in theory is not what is really working and what corresponds to the actual implementation. But that's my impression.
But the point is well taken, I think, that we have to check somehow that this is finding the global minimum, and we can do that. We can build up using Tribond or something like that and compare to the solutions here. But the advantage of this is that it's doing this k-lateration, and so we know how to get that solution. What we're really looking at is the search over the combinatorial space. We have to understand what the shape of that surface looks like. It's linear in A, so there may be something there. So in terms of thinking about what the cost surface looks like as a function of A, I think that might be one way to think about it.
By the way, Leo, you mentioned semi-infinite programming. We are competing with a big semi-infinite programming conference going on right now.
Yeah. Okay.
I guess you knew that.
So yeah, well, no, I have been
Anyway.
dragged into this. I'm allergic to infinities in mathematical programming, and I've been dragged into this thing by applications, industrial partners who really wanted something that couldn't be done without, or PhD students who got into that interest and then dragged me into it. So I'm sort of reticent and unwilling, but I did find certain things that were very interesting. For example, the moment SOS reformulations, they look magic to me because you reason about the moment problem, which is infinite, and then you can prove these weird, I mean, they're not weird, but they are strong duals because they are essentially duals on infinite LPs, but they correspond to a finitely representable polynomial program, which is non-convex. And so it's a mystery to me that you could derive a workable strong dual to something so haphazard. But there we have it. And so yes, some of the things that I exploited in order to solve that problem was effectively a moment style reformulation, which was much simpler than the whole theory, because the problem itself, I mean, the problem itself is just square second degree.
I have a question.
Please.
Can we look at the what was the definition in the distance geometry of a generic list?
Yeah, here it is here. So there were two statements. The second one is the one I emphasized, and that is, if I have a precise distance list, which is complete, and I form a clique from it of size greater than k plus 2, that is compatible, meaning that the distances fit together without error or without conflict, then all such cliques do appear in the final complete reconstruction.
Okay.
Does that make sense?
Yeah. So I mean, the definition is almost saying that when I run this algorithm, it does the right thing.
Yeah, right. It's like the generic rigidity statement in the sense that you just exclude all geometric.
No, but you don't know. I mean, it's possible. I mean, it's not true, but one could wonder whether does any graph have a generic distance list?
Yeah, right. Yeah, that's
Maybe
right.
K10 does not have a generic distance list inside of it for any framework. I placed the points at random, but somehow the algorithm won't work.
Yeah, that would have been my fear when I first started this, but we have seen that when we do this k-lateration process and we find cores, we almost never find cases where those things are not in the final structure. So in practice, they're rare. That doesn't mean that they don't occur. So that's really where we are. I'd love to see some proof that with high probability, a random point set produces distance lists that are generic. That's what I would love to know, but I don't know how to even get started on that proof.